As I have told you in the previous session that if the operating line and equilibrium line both are linear, we do not have to even go for the staircase graphical construction of staircase between this operating and equilibrium line. We can directly have the expressions of this number of stages, right, necessary to perform a given duty. So, that is called the Cremser-Brown-Sauder equation. So, we are going to discuss about this Cremser-Brown-Sauder equation. Yeah, Cremser-Brown and Sauder equation. So, you see, just let us have say this is tray n, this is the top of the column, here we have Ls and x0, here we have Gs and y1, and we are writing a balance over this envelope. So, this is Gs yn plus 1, this is Lx xn. So, we can write this Gs into yn plus 1 minus y1 Ls xn minus x0. Originally, this was derived for absorption only, but later it was observed that this can be readily utilized for other mass exchanges as well, right. So, we have yn plus 1 minus y1 is equal to Ls by Gs. Here we can write yn divided by alpha, where let us write the equilibrium relation is yn is equal to alpha xn, a linear equilibrium relation. Otherwise, this equation we cannot apply. So, minus x0, right. So, Ls divided by Gs into alpha this yn minus Ls divided by Gs into x0. Now, this quantity has got a significance. What is that? It is Ls divided by Gs divided by alpha. So, we can write that this is the slope of operating line divided by the slope of equilibrium line, and technically it is called absorption factor. Factor represented by A. So, you can write, see, if they are parallel, A is equal to 1, and we will see that for A equal to 1, Cremser-Brown-Sauder equation will not be applicable, because in the denominator of this expression of capital N, which is the number of stages required to perform the given duty, there appears log A. So, log A equal to 1, so denominator becomes 0, so it is a singular expression. So, Cremser-Brown is specifically valid for non-parallel but linear equilibrium and operating lines. So, you see that this we can write as Ayn, and this we can write as A into alpha into x0, because Ls by Gs divided by alpha is A. So, this becomes A into alpha. So, my structure of equation is yn plus 1 minus Ayn is equal to y1 minus A alpha x naught. So, this is a typical first order linear non-homogeneous difference equation. Right. And we can solve it very similarly to this technique what we have used to solve this first order linear non-homogeneous differential equation upon breaking the solution into complementary function, which is a solution of homogeneous part, and particular integral, which is a solution of non-homogeneous part. Here the same technique or similar technique can be applied. So, we have to go for a trial solution. So, homogeneous, so a solution of homogeneous part, which is y n plus 1 minus a y n is equal to 0. The trial solution is y n is equal to k 1 into z to the power n. So, k 1 into z to the power n plus 1 minus a into k 1 into z to the power n equal to 0. So, k 1 into z to the power n, so z minus a equal to 0. So, obvious conclusion is z equal to a. So, y n equal to k 1 into a to the power n. Next, the solution of non-homogeneous part. Here you see that here the solution is a constant, because the right hand side itself is constant. Let it be k 2. So, k 2 minus a k 2 is equal to y 1 minus a alpha x naught. So, k 2 equal to y 1 minus a alpha x naught divided by 1 minus a. So, overall solution y n is equal to k 1 into a to the power n plus y 1 minus a alpha x naught divided by 1 minus a. Now, we have to solve for k 1. See, if we set n equal to 0, if we set n equal to 0, then it will be y 0, which is alpha into x 0. This y n will be y 0, which is alpha into x 0. So, alpha into x 0 equal to k 1 into a to the power 0 minus y 1 minus a alpha x 0 divided by 1 minus a. So, k 1 is equal to alpha x 0 plus y 1, a to the power 0 is 1, y 1 minus a alpha x 0 divided by 1 minus a. So, this is alpha x 0 minus alpha a x 0 plus y 1 minus a alpha x 0 divided by 1 minus a. So, this and this cancels out, giving you y 1 plus alpha x 0 divided by 1 minus a. Correct? So, let me check. Yeah, this is a mistake, this is plus. So, here it will be minus and this is plus. So, that is why it cancels out. So, here the solution is alpha x 0 minus y 1. So, our final solution becomes this y n is equal to alpha x 0 minus y 1 divided by 1 minus a into a to the power n plus y 1 minus a alpha x 0 divided by 1 minus a. So, if I now write n is equal to n plus 1, then it will be y n plus 1 is equal to alpha x 0 minus y 1 divided by 1 minus a into a to the power n plus 1 plus y 1 minus a alpha x 0 divided by 1 minus a. So, we switch 1 plus y y1 minus a alpha x0, 1 minus a divided by alpha x0 minus y1 by 1 minus a is equal to a to the power n plus 1. So, we will have to take the log in order to get n, and an algebraic simplification will give you log of yn plus 1 minus alpha x0 divided by y1 minus alpha x0 into 1 minus 1 by a plus 1 by a divided by log of a. So, that is the final expression of Cremser-Brown's order equation, right. Yeah. So, this equation you see cannot be applied for a equal to 1, right, where these operating line and equilibrium lines are parallel to each other. Now, question is, at the bottom and at the top of a mass exchanger, that is a column, we have change in this equilibrium relation because the temperature changes, and naturally this equilibrium constant alpha may change, right. So, if alpha varies, then a bar you use a mean which is a1 into an, geometric mean of the top and the bottom, and with that you can safely use this Cremser-Brown equation, Cremser-Brown's order or KBS equation. So, this equation is equally valid for stripping and other these mass exchangers where this equilibrium and operating line are non-parallel but linear. Now, what happens if a is equal to 1? What will be my expression? Actually, we do not have to go for any solution, we can from the geometry we can actually solve. You see that if it is a linear equilibrium line and linear but parallel operating line. So, this is x0, this is y1, this is yn plus 1 and this is xn. So, we will have n, you see actually we have to go by staircase, this, right. So, from the liquid, from the gas side, what is the overall difference of y? Yn plus 1 minus y1, and individually as these two lines are parallel, this and this, they are all same, this are all same, right. So, here this is x0, so this is alpha x0. So, you can write our first expression as y1 minus alpha x0 because this much is y1 minus alpha x0. Now, what will be that? This is yn plus 1, this is xn. So, xn means alpha xn here, this point. So, this gap is yn plus 1 minus alpha xn. So, we have an alternative expression y1 divided by yn plus 1 minus alpha xn. And same is true for liquid because the horizontal gaps or horizontal extension in each stair, they are also identical. So, here you see this is x0, this is y1. So, this must be y1 divided by alpha. So, you can write another expression as the overall is xn minus x0 divided by y1 by alpha minus x0. And alternatively, this is yn. So, here this and also this, they are same, though it is outside, and here this is yn plus 1 divided by alpha. right. So, the gap is yn plus 1 by alpha minus xn. So, we can also write xn minus x0 divided by this yn plus 1 by alpha minus xn. So, there are 4 expressions in case of parallel operating and equilibrium line. So, these are the basic, very basic analytical idea about the solution regarding the number of stages. First, we have used the staircase, that is a graphical technique. We can also go by analytical technique, but there is a stage wise calculation. We can write a code. If you wish, you can write a code with a loop, with a for loop in C, and it will go on calculating, and there will be an if statement where we have to check that yn, small n, whether it is greater than y capital N plus 1, that is the inlet gas composition, and there will stop and will generate that will be the required number of stages. So, you can write a code. Alternatively, if these two lines are parallel, we can use this equation, or if they are linear but not parallel, we can use Cremser-Brown's order equations. So, there are 4 alternative cases we have discussed. Now, let us discuss about the construction, engineering constructions of trays. Right. The shell and all, I will not go into the detail, but here we will discuss the very basic regarding the construction. Now, there are we can have 3 different types of trays in common. That is a bubble cap, sieve plate, and valve trays. Now, you see the bubble cap, the oldest one, still in use, and there are 2 parts. One is a riser or chimney, and 2 is the cap. So, how it looks like? See, if this is your tray deck, you drill a hole, right? This is the tray deck. You drill a hole. Generally, for a bubble cap, the dimension varies from 1 inch to 6 inch. And next, there will be a chimney. How the chimney looks like? Chimney is like this. The bottom part is flared, and here we have an extension. Right, with a hole here. So, that is the chimney. It looks like this. So, we have to insert it here. In sectional view, it will look like this. The flared part, and here we have an O-ring. There is a gasket basically. Right. And on the top, here we have a bolt hole. So, we attach a cap. The cap looks like this. These are opening or slots. And there is a bolt hole at the top, right? So, you simply mount it and lock it through this bolt joint. So, this region, there is a gap, right, within the base and this bottom part of the slot. It is called shroud ring. So, you put this cap here. and here we have this bolt, right, and we have the slots here. It's not exactly the section, but for understanding I am drawing like this, and the liquid, you see, it will fill up the space like this. Now the gas will move through the chimney and it will move out, right, here it will move out. It has to form bubble and the bubble will pass like this. So through this residence time it will exchange, first it will move down and will find out the slot, and through the slot opening it will again move up through the pool of the liquid, which is the hydraulic depth we have to maintain here. There is a liquid pool height. So that's the cap, bolt, this is the shroud ring, this is the deck, this is the clearance we have to maintain, this is the chimney, and that's the tray deck. So this is overall the bubble cap arrangement, and there are different variations in design, but this is the basic one with which we can actually go for an efficient, very efficient mass exchange. However, you see the bubble cap, if you arrange this tray, like tray, here we have a bubble cap, here cap, here cap. So it offers high resistance to liquids, right, flow of liquid. Though it actually allows this higher residence time, but it offers a higher resistance because the liquid has to flow from this side to this side, and the flow is favored by hydraulic gradient. As we have noted, the design of this tray column, because one side we have the downcomer, incoming downcomer, another side we have the outgoing downcomer, and to maintain the pool height, we will discuss about it. We have the weirs, the downcomers, one of the wall is extended, right, and it maintains the pool height and hydraulic gradient throughout the tray. So that's the bubble cap arrangement. However, as it offers a high resistance to the liquid, there are heterogeneity in this flow of liquid through this individual tray, and that's why we move to the sieve plate. Sieve plate, you see, if you look into this plate, this is the incoming downcomer and outgoing downcomer, and here we punch the sieve basically, and sieves are arranged generally in triangular pitch. Like this, right? And here you see this is the weir of outgoing or draining downcomer, the liquid flows from this side and it goes here, and over this region, right, we have no sieves, and this is called calming zone. This is the shell, right, and the incoming downcomer area, a downcomer projection area and all. Now these sieves, you see, it's simply open, right? Here in the bubble cap, if the liquid has to percolate through the chimney, it has to move above and over this, this height, okay? So weeping of the liquid, which is a non-ideality, that means whenever the gas pressure decreases, the liquid may weep, but in bubble cap it will not weep if you have maintained a definite hydraulic gradient, but that may be a problem in sieve. Though you are saving a capital cost, but you are allowing this weeping if you have low gas velocity. Generally, these sieve holes, their dimensions is half inch to 1/8 inch, right, and common dimension for clean liquid is 3/8 inch. For scale forming liquid, we may go up to half inch. For vacuum service, where the weeping is highly probable, we have to reduce this opening. It is 1/8 inch, right. So, it moves from one end to another end. So, that is the two classical types of these trays we use. One is a bubble cap, another is a sieve. Now, what is valve? Valve is relatively more recent type of tray design, and it is till date it is a proprietary item, that means it is patented. The valve tray has an advantage over this bubble cap and the sieve, as it offers nearly invariant gas phase mass transfer coefficient upon adjusting the gas velocity. Even if the gas charging rate in that column drops, it will adjust the same gas velocity as with which we have designed the column. How come it is possible? So, valve tray, you see, and another additional specification regarding the sieve, that pitch, that is hole to hole distance, is 2.5 dH to 5 dH, where dH is the hole diameter. Right, and the hole diameter may vary, and accordingly we have to adjust this pitch, and it is triangular pitch. We generally recommend for the sieve tray, otherwise we will not have high interfacial area being generated between this gas and the liquid. Now, regarding the valve tray, see, the valve tray is one of the valve tray. It looks like this, simply this. These are extension of the legs. Like this. So, you see that these extensions actually hold this cap in the tray, because if this is the tray deck, the valve, this looks like this. This is a plate and this is the extensions, what I have drawn. And this region, through this region, the gas actually percolates into the pool of liquid, forming bubbles. Now, what happens if I have a high gas velocity? So, let us say initially the valves are all closed, right, because of the pool depth and the respective static pressure, this extension plates, and these are called guide vanes, guides. So, these are basically these guides, and what happens initially when we have zero gas velocity, this extension disk, they are having contacts with this tray deck. Now, we have charged the gas, right, at a definite pressure. So, this disk will pop up, allowing the gas to flow out into that pool of liquid. The point is, if I go on changing the gas velocity, this gap through which the gap actually, you see the gap is like this. Here we have the disk, here this is the tray deck, right, and this is the gap through which the gas flows out, right. So, this gap, this region, this area is being adjusted. Wherever we have a high pressure, that means we have a high gas charging rate into that column. So, this gap increases, right, and as the gap increases, the hatched area increases. So, gas velocity decreases. But if I have a low pressure, that means a low gas charging velocity, then definitely the gap is adjusted, the gap lowers down, area decreases, so velocity increases. So, more or less the velocity over a wide variation of gas charging rate into that column remains identical, and which gives you nearly similar or same regime of gas phase mass transfer, right. So, gas velocity as it remains same, its residence times of the gas bubbles remain same, right. So, it is invariant of that gas charging rate into that column, and that is the basic advantage of valve plates, and that is why it is called, it is alternatively referred as variable area plates. So, this is a discussion about the construction of the trays. So, you see that after that, once we have discussed about the three different type of trays, let us discuss about the downcomers and weirs. The downcomer, the basic construction, already we have an idea, like if this is the sectional view of the column, this is a single tray, this is the downcomer, and here it is the delivering downcomer into that column, here we have another tray. So, here we have an inlet weir, right. So, the liquid from this tray moves to the downcomer, and here we have the weir. This extension is called weir height, right. This is the downcomer, right. So, actually in 3D it looks like this. And there is a slot which we can fix by bolts, and this is the downcomer plate, and this weir we can adjust, right, in that slot upon adjusting the screw, and we can keep this height changing, right, similar here. So, what happens, why this height is being changed? Because the liquid from here, it will flow out, and a hydraulic gradient, here height is H1, here the weir height and the respective liquid height is H2, H1 must be higher than H2, and there is a progressive decrease of the liquid depth over the pool. Why? Because you see, there is an open flow, and to facilitate that open flow we need a hydraulic gradient, right. A hydraulic gradient is necessary. However, if I have a very high hydraulic gradient, like liquid depth is here high and here low, so the gas bubble majorly pass through these regions, and eventually the gas bubble will be entrained into the downcomer, right, and this part of the tray will remain ineffective. So, if the hydraulic gradient is not properly adjusted, it may cause severe non-ideality in this operation. So, generally the hydraulic gradient should be kept less than ½ inch, very low, and based on that we have a more or less uniform distribution of these gas bubbles throughout the entire this passage of this liquid, right. So, these slots we adjust, and let us say these are the sieves, right. So, the liquid will move out like this and it will fall into the downcomer and goes to the next plate. Now, you see this downcomer, it has got varying volume. Why? Because for clean liquid, generally the residence time in the downcomer varies between 3 to 5 seconds, right, and respectively it gives rise to a velocity 0.3 to 0.5 feet per second, something like that, in the order of 0.3 to 0.5, let me check, 0.3 to 0.5 feet per second. Yeah. So, if the liquid is froth forming liquid, like it has got a very low interfacial and the gas and liquid has got a very low interfacial tension, then there will be froth. And for froth forming liquid, the downcomer volume should be larger. Why? Because the downcomer, one of the top part of the downcomer actually separates the entrained gas bubbles from the liquid, and that is why we have a reduction in this cross sectional area as the liquid flows down. Like here, we can have some entrained bubbles, but that must separate out after moving certain distance, because there is a kind of bottleneck here as we are reducing this. So, only liquid is allowed to pass to the next tray, and the entrained gas bubbles, if any, will again move back. Okay. So, point is that if the liquid is froth forming liquid, or if the gas and liquid they have froth forming tendency, then the downcomer volume should be increased. Okay. Now, in relation to this downcomer wear and this wear height and all, hydraulic gradient, everything, we must discuss a non-ideality called flooding in packed column. But before we go into that flooding, let me tell you that this downcomer, you see, here we have the incoming downcomer projected area, outgoing downcomer projected area. This individual downcomer area varies from 5 to 15%, right. So, on both sides we have this projected area which are to be sealed. There should not be any sieve or bubble cap here, right. And additionally we have this coming zone, and here from after a certain clearance we should drill the sieve, if I am using sieve, or the bubble cap we should place. So, effective area is around 70 to 90% of the total tray area, over which actually this mass transfer takes place. Okay. Because 5% and 5%, a bit higher, basically we are having coming zones. So, it is not 90, it may be 85%, and here it is still lower, let us say 65%. So, 65 to 85% of this tray area varying based on whether it is froth forming or clean liquid, we have the effective mass transfer area over this column cross section. So, and this wear length may vary as 60 to 80% of this tower diameter, and correspondingly this corresponds to 50 to 15%. Like this wear length is 60 to 80% of the tower diameter, 0.6 to 0.8 tower diameter, and actually you see that once we have given this downcomer area, like 15% is very common, right. So, if it is fixed at 15%, we can actually determine the wear length which is nothing but a chord to this circle. Like this is the wavelength, right. This area you see it's 15%, right. So, and the tower radius is r. Okay. So, if I can solve for this theta, I can actually calculate this wavelength. So, 15% means, you see, what is the area? This is say theta and this is also theta. So, for 2 pi it gives you the total area of pi r square. So, for 2 theta it is pi r square divided simple unitary method 2 pi multiplied by 2 theta, which is theta into r square, right. That is the total area, this and this, right. Next we have to subtract the area of the triangle. So, theta into r square minus half r square into sine 2 theta, which is the area of the triangle, because triangles with sides a and b and intermediate angle theta, the area is half ab sine theta. So, you have used half of r square sine 2 theta. So, this is the hatched area, that divided by pi r square is basically 15%. So, 0.15. So, it is a transcendental equation from which we can solve this theta, and the wavelength will be this r, and here it is theta. So, twice of r sine theta, right. So, you can calculate the wavelength, and when it is 15%, I am saying that 5 to 15%, the chord length of this wave or the respective wavelength varies between this 0.6 to 0.8 of the tower diameter. So, that is the idea of the downcomer, wear and all, hydraulic gradients and how to adjust this wear height, why wear height is important to maintain the hydraulic gradient, and the maximum hydraulic gradient which we should operate a column is around ½ inch. Now, the point is flooding. So, here it is flooding in a tray column, right. So, there are 3 different types of flooding. Unlike packed column, here we can have only one specific flooding. Now, what is flooding and why there are 3 different types? Flooding is a non-ideality which leads to excessive accumulation of this liquid, right, in a column, where the liquid flow is not smooth and it is blocked at some point by some non-ideality. Then the liquid starts accumulating because you are continuously delivering liquid and liquid is unable to drain out from the column. So, there will be accumulation of liquid, right. And that whenever the liquid starts accumulating, what will happen? What will happen? Previously, it was liquid this continuous and gas dispersed phase, and when the liquid starts accumulating and there was certain pressure drop because you were maintaining a definite hydraulic gradient and the liquid pool depth over every tray. The liquid pool height over the tray increases, right, and the downcomer chokes, and what will happen? The gas pressure drop will tremendously increase, leading to non-ideality. So, what are the different types of flooding? So, first one is called spray entrainment flooding. What is that? See, from one downcomer over the tray, the liquid has to follow the path to another downcomer. Now, if the liquid pool height is low, right, the pool height itself is low, what will happen? I have adjusted the wear to have a high hydraulic gradient, but to this pool height is low, and what will happen? And if the gas velocity is high, right, the gas will eject the liquid because of its high velocity in the form of drops, and it will be transported or entrained in the form of spray through this tray above, and the liquid flow ceases here, right, and liquid starts accumulating and flows back, and additionally we have the augmentation of the spray from this bottom. So, liquid starts accumulating, and this is called spray entrainment flooding, which is probable for low liquid flow rate, low pool depth, right. Low liquid flow rate may not be the case, it is the low liquid pool height over the tray and high gas velocity. Second, froth flooding, froth entrainment, or what is the exact name? Yeah, froth entrainment flooding. Right. So, here we have a low surface tension, or rather the interfacial tension between the liquid and gas, and when the liquid flows, the gas having contact, it forms froth, and the froth grows in size, it entraps the liquid in it, and finally, in case of extreme feature, it may percolate into the tray above, right. So, this is the froth entrainment flooding. Why the flooding is actually happening? Because of froth formation. The froth entraps the liquid whatever it receives from this incoming downcomer, and that froth actually, so this froth floods the previous or this tray above, so it percolates, and this in that froth the liquid gets arrested, okay, and liquid accumulation, but because you are delivering liquid continuously into the tower, so the liquid accumulation starts and the flooding happens. The most common type of flooding is called downcomer flooding. Right. See, the downcomer, there is a reduction in cross sectional area as I have mentioned, because the upper part, if any gas bubble is entrained into the downcomer, we have to contract the section, we have to create a bottleneck such that this gas bubble flows out, right. But this at the same time may be leading to flooding, right. How come it happens? You have seen that in a funnel, right, in a funnel looks like the downcomer here because there is a reduction in cross sectional area. Let us say I am pouring some liquid in the bottle through a funnel. So, if I pour a large amount of liquid, what will happen? The funnel will choke and the liquid will flow out, right. So, if the liquid flow rate is high and the downcomer area is not properly designed, what will happen? The downcomer may choke and the liquid will flow out, right. But the liquid flow rate is high, so what will happen? The liquid starts accumulating here or the tray above or the tray above. So, in this way the flooding is promoted. Okay. So, there are three different types of flooding: spray entrainment flooding, froth entrainment flooding, and downcomer flooding. Downcomer flooding has got certain geometric conditions based on the weir height, which I am not discussing right now. Now, this flooding primarily depends on the liquid flow rate, gas velocity, etc. Now, how to actually fix this tower cross sectional area? Because flooding velocity is a gas velocity which is the limiting velocity, right. So, there is a method called Fair's method, which was proposed by Sauder and Brown, right, based on spray entrainment flooding. What they have proposed? That flooding velocity is equal to CSB into under root of rho L minus rho G divided by rho G, right. And this CSB depends on this gas and liquid flow rate. There are charts by which we can determine it. But over a large range of this gas and liquid flow, the CSB we can consider to be constant. This is called Sauder-Brown flooding constant. Actually, it depends on the gas and liquid velocity, right. So, based on this equation, the CSB, there are log plots of different with respect to different empirical variables, right, or variables, and that plot is empirical. So, from there we can get the value of Sauter-Brown flooding constant. Now, the point is this depends, as you can see, this depends on the pressure, right, the column pressure, and we can approximate this equation as CSB into rho L by rho G. There was a question, a GET question, like as I am increasing the column pressure, how the flooding velocity will change. So, rho G we can write as Pm divided by RT considering ideal gas equation, and from there we can establish that flooding velocity is tentatively proportional to under 1 by divided by under root of column pressure, right. Now, the point is, once you know the flooding velocity, next 60 to the operating velocity will be 60 to 80% of this flooding velocity, right. 60 to 80% of this flooding velocity will be the operating velocity. So, U operating is this 0.6 to 0.8 of U flooding, right. Now, based on this operating velocity, definitely we can determine the column cross sectional area. Let the downcomer or single downcomer area fraction is A, right. So, G, the gas velocity, divided by the column total column cross sectional area into 1 minus 2f, because the downcomer individual downcomer area, let the single downcomer area fraction is f, sorry. So, this is the total column cross sectional area. So, A into 1 minus 2f is equal to U this operating, right, which is some fraction into the flooding velocity, which is 0.6 to 0.8 of flooding velocity. Now, from there we can calculate the cross sectional area, and from there this tower diameter, d tower square, right. So, this is the calculation of this tower diameter, and it is an important equation in the design. However, you have to note that this is based on spray entrainment flooding, but in undergrad level for standard problem solving, we mostly work with this equation actually, right. The CSB is called the Sauter-Brown flooding constant. In reality, CSB is not a constant. It depends upon the tray spacing, liquid load, fractional hole area on the tray, and the hole diameter. CSB can be obtained from a log chart of CSB and flow parameter Lg by L divided by G, rho G by rho L root of this. So, this will be giving you a log plot of CSB and flow parameter FLV, which is L divided by G into rho G by rho L to the power 0.5. So, this is a log plot. I am not going into the details of that. So, it is not important because it is empirical. So, anyway, so that is all about the tray column. Next, we will discuss about the packed column, and similarly how to design the area of the packed column, and the packed column height will be based on the specific type of operation what we are dealing with. After maybe in the next session, we will be discussing about how to determine the packing height in case of absorption, right. But before going into that, let us discuss about the basic engineering internals and components of packed column. So, you see in the packed column, from the bottom we have a nozzle, right, and yeah, from the top we have the gas outlet, and here we deliver the liquid. Yeah, we deliver the liquid, and there is a distribution system. Like this, this, and similarly this one, right. So, this is the liquid inlet, gas outlet, then we have the liquid distribution system, next we have the packing, right, and the packing, it may be structured. There are two different types of packing, random, we will discuss about it, and structured packing. Say this is the packing over a segment. However, you see that for a tall column we cannot extend the packing continuously to the bottom. Why? Because there will be problems of this non-homogeneous distribution of the liquid, and if I have the liquid majorly flowing down through this region, a specific region where the resistances are low, and the gas will move out to the other part. So, there is insignificant gas liquid contact. As a consequence, we will have the drop of column efficiency. So, the drop of column efficiency, in order to these are non-idealities called channeling, then liquid non-homogeneous distribution. So, over a certain segment we have to break the packing, and again we have to redistribute the liquid. So, how this redistribution is being done? There is a tray, and we have this sort of protrusions, right, pipes which are fitted like this. So, liquid will accumulate over the tray and again flow through these pipes which are uniformly placed here. So, this is a liquid redistribution system, and again we will have the packing here, right, and at this point we have this gas injection system. So, it looks like this. This is a specific type of gas injection system, and here we have openings so that the gas is uniformly distributed over the entire cross section, right, and again we have packing here. So, gas will move like this, will be homogeneously distributed, and at the bottom we have the liquid pool, and we should have this gas inlet somewhere here. So, this is the gas inlet, right. So, that is more or less the pack tower. Now, there are different types of these packing materials, as I mentioned, random packing. Random packings, which we have seen that they may be this Rashig ring, there are first generation, second generation, that based on the complexity basically of the structure, and third generation packing material. The first generation example is a Rashig ring. These are small plastic or ceramic tubes or ceramic this segment, which is a hollow cylinder type, right. Rashig ring, This is called Rashigring. Right. There are ball saddle, there are interlock saddles. So, there are different proprietary saddles, examples of this random packing, like the common packing elements of random packing materials, a Rashigring, which we have discussed. That ball saddle, it looks like this. This is a ball saddle typical. Right. And nowadays we have the flexibility of this molding and all. An advantage in molding give rise to different types of complex geometries in this random packing design, and that is why this first generation, this ball saddle, Rashigring, they are first generation packing elements. We have second generations, third generations, etc. Second generations are this typical interlock saddle, then nutter ring, jagger ring, Koch flexi saddle. These are third generation packing. We do not have to remember these names, right? But just note this Rashigring and ball saddle as a typical example of this random packing material. Now, where alternative to this, we have structured packing, right? And structured packing, it came into use from 1980s onwards, and they are nowadays the competitors of these random packings, right? What is the structured packing like? You see, this is the column section, and we have this corrugated metal sheet or plastic sheet, right? This, and with perforations, of course, right. So, 2-3 layers will be like this, and after that we will change the orientation like here, and again 3-4 layers like this, and again this opposite. So, these are structured packing, which actually gives much lower pressure drop and high interfacial area relative to this random packing. But again, this capital cost in the structured packing is high. So, higher initial cost of such packing is amply compensated by lesser operating cost because of lesser pressure drop across the beds. So, these are the different types of the packing. Now, similar to tray column, here also in pack column we have the non-ideality of flooding. So, what is flooding here? Here you see that as you go on increasing the gas velocity, the liquid flow will be highly impeded, right? And the liquid will start accumulating over some region of that column for a specific type of gas velocity. And this we generally try to understand through a log-log plot of this pressure drop and the gas flow rate for different liquid flow rates. So, here what we plot. So, this is flooding in packed column, right. So, log of delta P, the gas phase pressure drop, is log of G, right. Now, see that if I think of this Burke-Plummer equation, then 1.75, because this is not a laminar flow, this will be definitely turbulent flow, rho into V bar square 1 minus epsilon divided by epsilon cube phi into dP whole square, right. So, now phi into dP, I think, yeah. So, this is the Burke-Plummer equation of packed bed, right, pressure drop in packed bed, where we have no liquid flow. So, log of delta P is proportional to log of V, right. So, we will have a straight line with a slope of this 2, there will be slope 2 because of this power. So, this is a pressure drop curve where L equal to 0. Now, when we have an L, then the curve that changes to this sort of pattern. This is a pattern, right. Initially, and for still higher liquid flow rate, this is the pattern. So, let us say there are 3 different points B, B prime, then C, C prime, D, D prime, etc. Initially, over a certain region, this is parallel, nearly parallel. Actually, this will be like this. Let me draw it afresh. Something like this, something like this, yes. B, B prime, then C, C prime, then D, D prime, right. So, this is L1, this is L2, L2 is higher than L1. So, initially over some region for low gas velocity, this will be nearly parallel to this dry bed pressure drop versus log G curve, right. Because the liquid flow rate is low, the gas velocity is also low. After some point, the pressure drop starts increasing, further it increases and then it goes down to some extent. So, when it starts increasing, there is a discontinuity in the derivative, and that is called onset of loading, which means the liquid accumulation just has started, and this is the loading region of this curve, right. Flooding means excessive amount of liquid accumulation. This is called the onset of flooding, that is incipient flooding, right, and that is the flooding region where the liquid accumulation is huge, and because of that what happens, you see that if in a packed bed we know it is a liquid discontinuous, gas continuous contacting pattern, right, we have in packed bed. But if the liquid starts accumulating here, the liquid actually will fill up the space between these pores and all will be filled up by this liquid. The spaces between the packing will be entirely filled up by the liquid, and through which the gas will be passing as a discontinuous or dispersed phase, right. So, there will be a tremendous drop of mass transfer efficiency, because the packed bed we intentionally have used or chosen to increase the mass transfer efficiency, because in that specific case it is a liquid phase, the gas phase has got the controlling resistance. Okay. The component A is highly soluble in the liquid. So, gas phase has got the controlling resistance. So, gas phase must be continuous. But if we have flooding in packed bed, the liquid actually starts accumulating in the bed. The liquid will fill up the space, the void space in this packing, right, and through that void space the gas will actually be forming the bubble, because it has to pass through the pool of liquid whatever is accumulated. So, there will be a severe drop of mass transfer efficiency, and that is why flooding in packed bed is sometimes defined, it is a region of rapidly increasing pressure drop with simultaneous loss of mass transfer efficiency. This was a statement or the definition of, or the it's a kind of description of flooding as proposed by Bravo and Fair, right. So, the phenomena is flooding and the bed becomes flooded at this point D, right, and the void in the bed becomes full of liquid. From here we have the severe the change of this or the paradigm shift of this continuous and dispersed phase. Now the liquid becomes continuous, the gas becomes dispersed, and as a consequence the mass transfer efficiency tremendously drops. So that's about the construction of the packed bed and the engineering constructions of this packed bed, and this previously we have discussed about the tray columns, different types of these trays, the role of downcomer, then weirs, hydraulic gradients, everything we have discussed. So in the next session we are going to discuss about absorption and how to determine the packing height specifically in case of absorption.